All right, class, time to get started. Okay, so announcements for today, pretty much the same as they were on Monday. Just as a reminder, we have a lot of things coming up. So wanted to make sure we hit on all of them. Hold on, let me get this out of the way. Homework 10 due today, homework 11 will be assigned today. And that's the last one, right? So that's going to cover all the material through the end of chapter 9, or through the end of what we're covering in chapter 9. Will be on homework 11. So that will include some material that we may get to today, or that we may end up covering on Friday, depending on how things go. But that homework will be assigned today. Reminder: your final project is due next Wednesday, the last day of class. Please get your projects going if you have not already. So please make sure you're working with your groups and get started on that, Michael.
So, you want to do at least 5 pages. That seems like a lot for how much we're actually doing. Those 5 pages include like any graphical elements?
Yeah, the 5 pages includes graphical elements that you put in there. Yeah, it's not pages of solid text, but there is some writing that I am looking for on comparison. You know, for example, to the published results, right? To the literature results you find. Also, just descriptions of what's in the plots, right? So just putting a plot. So in the tutorial, I was really just looking for those plots, right? And everybody got 100% because I went through and checked all of those, just looked for all those plots. But no commentary necessary on tutorial. On the report, on the part 2, I do expect discussion of what's in the plots. Yeah, you may have to do more than what the project tells you to do in order to the 2 elements that are highlighted as being very important about your results in the CFD part 2 assignment are the verification, where you're comparing to literature results, and the grid convergence study, right, where you're actually telling me that your solution is grid independent, or that as you increase the density of your grid, your answer does not change, right? Depending on which exactly project you were assigned, there may be already some validation, some verification built into that assignment or not. There may be some grid independence built into that study or not, but I'm expecting to see both of those things from all of you. So that means you'll have to go beyond what exactly is in the project tutorial that's listed for you. Yep.
Sorry to spend one more question, but with that, like how many like different
enough to show that it is actually really converging. So you know, with 3 points, you're really just making a line. So the question is about how many points do you need to show in order to show that you've really truly converged. There's no hard fast number, right? So I want to see evidence that you've truly converged, right? So if you have let's say you're computing the coefficient of lift in your simulation, and you're going to plot coefficient of lift versus a number of grid elements, right? So remember when we talked about CFD, we talked about there being multiple different types of convergence. So one thing to note, this is not, when you run a single CFD simulation, it will show you a convergence plot. That is convergence versus number of iterations. That is not the same thing as what I'm asking for here, okay? What I'm asking for here is something different. This is convergence relative to number of grid elements. So this is going to require multiple simulations, okay? And this is a case where most of you are going to have to go beyond what's in the, again, exactly what's in the tutorial, the project tutorials that you've been given. So let's say we're looking at coefficient of lift versus number of grid elements. You run this once, right? If you run the simulation once, look at your simulation after it's achieved numerical convergence, right, for that simulation. You'll get an answer. But now the question that we talked about was, how do you know that this answer is reasonable, right? How do we know that this answer is not affected by our number of grid elements? And the way that we're going to tell that is by looking for grid independence. So that means that you should, take the number of grid elements and increase it, like make your mesh finer. Typically, if you're following those tutorials, they've already directed you to a grid size that is converged, right? So the people who designed that tutorial probably did this already for you. So you're also going to have to go below and do some simulations below, right, with smaller grid elements. And I don't know, maybe 5 is a reasonable minimum, but I want to see this convergence behavior. So depending on what your spacing is, right, you could end up running 5 simulations and just show, the same result for all 5. So then I do want to see this convergence behavior. So that means, run a few more at very low grid to make sure that, to actually show this convergence behavior. Does that make sense? Okay. So there's not like some minimum number that I'm looking for, like, oh, you've done 5, check it off. What I'm looking for is to see clear convergence behavior. Okay, that's what I'm looking for. Does that make sense? This has sometimes been a cause of confusion on these projects, so I want to make sure you understand. But this is not the same, right? So this is not equal to when you looked at your plots of residuals, the plots that are automatically spit out from your solver are residuals versus number of iterations. And this is typically a log scale. And you'll see it coming down like this. And you'll see like plot residuals for a few different things. This plot that's automatically spit out by the solver is not the same as this. You're going to have to plot this yourself, Excel or Python or something. Okay, you're going to have to make this plot yourself. Okay. All right. Any questions on this? Yeah. So our exam is the first day of exams, Monday, the 12th. I'm not allowed to have anything due during the reading period. And so the first day I could make things due would be the day of your exam. And you should have the homework done before the exam, right, in time for us to grade. So no, what I'm saying is no, I don't really have much flexibility on due dates, unfortunately, for this class. Yeah, we could move to Thursday. I could move both to Thursday. Both the homework and the project. So I don't want to move just the project because then you're all going to start the project on Thursday morning. And that will not be enough time. So if you start the project on Wednesday of next week, you will not have enough time to finish it in one day. The project is going to take substantial time. Okay. To run and to show this is going to take time. Okay. Particularly if you have to increase, you will have to increase your grid size to show that you've actually converged. Those simulations will take time to run. There's a chance for some of your projects that you may need more elements than you can do in the student version. You're going to have to fire up the, I know slower version on the connect.chemeng accounts. So start this, okay? Start this early if you haven't already. Yep.
My project projects, it has this take a specific section of that of that thing and then increase the size. So would it be better to change the overall grid elements? Because I imagine if you get a number of grid elements, that would be more like to do this every day.
So I don't. So for this, yeah, number of grid elements. You can also plot 1 over the minimum grid size. For this tends to be easier to find. Okay, number of grid elements tends to be easier to find. 1 over a minimum grid size might be more relevant depending on what problem you're actually doing. Either of these is fine. Okay, just something that shows that you are grid converged, that as your grid is getting more refined, your answer is actually converging. Okay, and I'm really just trying to make sure that you get a flavor of this, right? So for an actual problem, right, where you're really designing a system, and that design depends on your CFD. You'd have to do quite a bit more validation of your solution and ensuring that you actually converge. But I just really want to give you a flavor of that. So any parameter related to grid, like number of grid elements, 1 over grid size, showing this convergence behavior. That's what I'm looking for. Okay. And so then on here, on here, we would say we would probably choose either this one or this one, right? If we were to then, run further simulations, right? So we would say, probably maybe here is grid independent, and therefore this is a fine enough grid for us to get an answer that we believe is not being affected by the grid size. Yep.
If we're going to do that, we got that one arrow next to the
Mm-hmm.
would we have to do another setup for that? We already did one before,
Yeah, you should keep going, just to make sure, because this is not, I've drawn this as a nice smooth curve. It's not always a nice smooth curve. Especially depending on how you do your refinement, this might not always be a nice smooth curve. So, this is data. It'll be noisy. Yeah. Okay. Yes.
And then with the convergence, you want us to give like a contour for each of the convergence models for each of those.
No, I don't need to see like a full plot for each one of these. What I want to see is you have to pull out some number. So this is other work that you're going to have to do, maybe independent of what's in your specific project statement. Is you have to pull out one number, right? One result from that simulation, right? So if it's an airfoil, it's something that's relevant to the problem. Okay. So if you're simulating an airfoil, maybe you want to know coefficient of lift, right? You're simulating, a drag on a car, maybe it's drag force or coefficient of drag. Okay. Yeah, just some parameters, some single numerical parameters, you can make this plot. You want to pull that up. Okay. All right. Any other questions? Okay. All right, so where we left off, so we just discussed compressible flow through a converging nozzle. All right, so we talked about what happens when we have flow from some stagnation condition upstream through some kind of a converging nozzle, exhausting into some kind of atmosphere outside. And remember, we said that, so a long time ago, we said that for a subsonic jet, the jet pressure is equal to the atmospheric pressure or the external pressure. And here we said what happens when we have a supersonic jet, right? When we have a supersonic jet, this exit pressure of the jet is not always equal to the atmospheric pressure, the pressure that it's exhausting into. Any questions on what we covered before, like this, or the other material from last class? So I'll just note this is also basically what happens if you put a hole in the side of a compressed gas tank, right? So imagine if this was a tank at some stagnation pressure P naught, we punch a hole in it. We basically created like a small little nozzle for exhaust. And so we could then figure out the mass flow rate, for example, that would be lost through that kind of a nozzle. So next up, we're going to talk about converging and diverging nozzles is the next topic. So we're going to take this and we're going to add an expansion on the outside, on the other side, and we're going to ask what happens. And again, we're going to look at what happens under operation of such a device where we have a fixed stagnation condition and we decrease the exhaust pressure, and we'll ask what happens. But before we do that, I just want to talk for a second about something that you've seen on your homework and that will come back, which is Reynolds number and estimating Reynolds number, right? So on your homework, you'll see that there's a question from a previous final, and it asks you to estimate Reynolds number and see if it's laminar, transitional, or turbulent for a whole bunch of different flow situations. You can expect that kind of problem on the final exam. And you'll see that that type of problem is on the 2021 final exam. So you'll see that when I release that for practice, which should be today or tomorrow. And you'll see that some of those are relatively straightforward. I give you basically all the parameters you need to compute Reynolds number more or less directly. Other problems you need to solve solve for velocity or solve for length or something. And some of them are really just about giving me an estimate. So on that exam, you'll see there's one question. There's one question which asks you, what is the Reynolds number for a flagpole in a hurricane? Yeah, but a reasonable guess. Okay. So, I don't want you telling me that a flagpole is 1 millimeter in diameter, right? That would be wrong. I don't want you telling me that the flagpole is 10 meters in diameter, right? So give me something reasonable. Yep.
So kind of like there are some of the questions like where you're dealing with spiritual objects, and like you could make the argument that the flow of it was lambda, but because it was when you stoke close to creeping flow, it had turbulence behind it in the wave.
In creeping flow, there would be absolutely no turbulence in the wave. So we're defined for external flow. How do we define when the flow is like, what's the transitional regime in external flow? Reynolds number based on length of what? 10 to the 5th to 10 to the 6th. So Reynolds number based on length, 10 to the 5th, 10 to the 6th, we call that transitional. So there may be a turbulent wake, but we're talking about the flow over the object. We call that in the transitional. We're going to call that in the transitional regime.
Okay.
Okay.
So we're more those questions more so asking like, are we in that regime?
Yep, I'm asking about the flow regime because remember, said many times if you don't know the Reynolds number, you don't know anything about the flow, right? So you have to be estimating Reynolds number, right, to understand what's going on. For a flagpole in the transitional regime, we're going to see different kinds of behavior than we see for a flagpole in a laminar regime or in a turbulent regime. Right? Qualitatively different behavior, right? We're going to see qualitatively different behavior depending on the flow regime. So that's why that flow regime is so important. Yep. Yeah, so just give me an approximate, so you say the speed is, 100 miles an hour or something. And the size of the flagpole is maybe 10 centimeters, right? And estimate Reynolds number. 10 centimeters, it's like 4 inches, right? Diameter. So yeah, that's another question, okay? So when you're estimating Reynolds number, like flagpole in a hurricane, then now remember on the exam, you're not allowed to use the internet, right? So you can't just Google diameter flagpole, wind speed hurricane, right? So, I really do want you to estimate it. That's an important skill for addressing a problem in fluids. So, estimate size and speed, look up property values, right? So I'm not telling you the property values of air. I'm just asking you again about flagpole and hurricane. So there's another example you saw in homework 9. It came from 2019 midterm. It concerned Lachlan Morton's power data in the tour of Utah in the previous year. And one of the questions on there, right? So this was a drag and power problem primarily, but there was a question there where I asked you to estimate the Reynolds number and tell me if it was laminar, transitional, or turbulent. And density and viscosity were given, right? So I told you density and viscosity based on the air temperature and elevation for the specific day when that problem was based on. And then you were asked in the problem to solve for rider velocity, or given enough information to solve for average velocity based on distance and time. But now to estimate Reynolds number, what else do we need? We need length. I didn't give you length, okay? So what would you use as length for estimating Reynolds number of a bike rider? 1 meter, right? About the length of a bike. That's pretty reasonable. 2 meters is a little long.
I was thinking more like the length of like the guy's
but now which direction matters, right? Which length matters? Yeah, along the flow, right? So the length along the flow is really what matters. So, half meter, right? Maybe diameter of a person and arms or whatever, up to maybe a meter or so, something like that was pretty reasonable. So to watch out, some of the answers, right? So now we need the length. I did get some inappropriate answers, like the length of the road was given in the problem. So some people estimated Reynolds number based on length of the road. That's absolutely not appropriate. The elevation was given in the problem. That would absolutely not be appropriate either. So appropriate length scales would be like 1 meter, 6 feet, 0.5 meters, something like that. Would be appropriate to estimate the Reynolds number for flow around this bike rider. Okay, does that make sense? That's something I do expect you to be able to do, right? Again, because if you don't know Reynolds number, you don't know anything, and there are qualitatively different behaviors for flows in laminar, transitional, and turbulent regimes, right? So in internal flow, so in external flow, we saw that for a for flow around a sphere, as we get to, for example, very high Reynolds numbers, or when we have turbulent flow, we typically see just a constant coefficient of drag. In the transitional regime, we saw that we have a really strong dependence on the roughness of the object, right? Where depending on the roughness of the object, we could trip, like with a golf ball, we can trip the flow to turbulent and dramatically reduce the wake, right? So knowing if you're in that transitional regime versus if you're in that turbulent regime is actually really important. And in internal flow, we saw that we had very different forms of the equations that we used to find the friction factor for laminar and turbulent. And we were going to try to avoid the transitional regime. So what's the transitional regime for internal flow? Somebody who didn't forget. Let's help Francisco. Yeah. So 2300 is a number. That's not a range. So what would be a range? Let's put a range on that number. What's a range for transition for internal flow? Yeah.
Like 2,000 to like 10,000.
Yeah, 2,000 to 10,000 or so would be a reasonable range for transition for internal flow. Okay. So if you're in that range, right? So if you had a Reynolds number of 2350, right? That is technically above that Reynolds number, that cutoff that we defined of that we were using as of 2300. But I don't know, if I were an engineer designing a system and I computed a Reynolds number of 2350, I would not be confident that it was turbulent, right? Because transition depends on many things, and you may not have fully turbulent. You may not have turbulent flow at 2350. Okay. Any questions on this? All right, so you get some practice on the on this homework, and I think I'm going to give you the other problem about estimating Reynolds number from the 2021 midterm on the next homework, which will be assigned today. So you'll see this and get a chance to practice this. It is kind of qualitatively a new type of problem that you haven't seen on an exam yet, right? So you've seen true false, you've seen problem setups, but I haven't asked you this kind of thing on an exam yet, but you should expect it. Okay. So as promised, we're going to talk about a converging diverging nozzle now, right? So last class, we talked about the case where we were accelerating flow from stagnation through a converging nozzle. And now we're going to look at basically the same thing with the addition of this diverging nozzle downstream. And now we're looking at what happens for the case of compressible flow in this kind of a situation. So just want to step back for a second. If we have just to review, so in this converging nozzle, if we start from stagnation, what's the maximum Mach number within the solid nozzle structure? Can I hear louder? I see something. Okay, 1. Yeah, 1 is a maximum Mach number. Why is the maximum Mach number within this nozzle 1? Yeah. Because we're going from subsonic to maybe a supersonic exhaust, and there's a local minimum of area right here, right at the very end. The very end is our local minimum, and at that point we can get to Mach number 1, but we can't go past Mach number 1 at that local minimum, right? So here the maximum Mach number was within the nozzle structure was 1. We could have supersonic jet. We didn't really talk. We're not really talking about the details of that supersonic jet, but we could have a supersonic jet. But within this structure, the maximum Mach number is 1. So now we're going to talk about adding what happens when we add this this expansion, and this is a way that we can actually get past Mach number of 1. So with this design, we can get past a Mach number of 1, and we're going to talk about that. We have, let's talk through what these different curves here are. So this again is a plot of pressure versus distance through the system, and it's aligned, right, with the system. So it's showing pressure at all those, at every X position within this nozzle system. And it's showing that pressure as we keep the stagnation pressure, the upstream pressure constant, and we lower the exit pressure, right? So it's like where, let's say we're exposing this to some condition downstream, and we're continually lowering the pressure, like lowering the atmospheric pressure, right? That's what's happening here as we move down in these curves. And so what it's showing is that if we start with a relatively small pressure difference, right, between stagnation and atmospheric or exit pressure, we'll first find ourselves along this curve A. And in curve A, the flow here is entirely subsonic. Okay, maybe compressible, right? So we may be achieving speeds that are high enough that the Mach number is greater than 0.3, and we have to include compressibility effects, but the flow is still entirely subsonic on this curve A. So on curve A, as we decrease area upstream, what's happening to the flow? Is the flow accelerating or decelerating through this region? Accelerating, right? Because for subsonic flow, as we decrease the area, right, the velocity has to go up, right? But now and for curve A, let's just talk about curve A. If we move into this region where we have the nozzle opening up an area, what's happening to the flow? The area is increasing, and is the flow decreasing or increasing in velocity? Decreasing in velocity, right? Because we're still subsonic here. Okay? Curve B is a lower outlet pressure, but we're still subsonic. Okay. So curve C shows the point where the pressure at the throat is exactly equal to P star. So P star is the pressure where the flow achieves Mach number 1. So if the pressure achieves P star exactly at the throat, then that means that the flow is now choked, right? Mach number is 1 at the throat. And curve C is showing this, kind of rare case where things are exactly perfectly set up, and the flow goes from, and the flow remains subsonic throughout. So even though we achieve Mach number 1 at the throat, it remains as we open up, right, the flow, as we open up the duct, increase the area of the duct, it remains subsonic. So in curve C, it's still decelerating as we open things up. Okay. But now these other curves here are where things get different, qualitatively different. And I want to start actually with curve H. So we're going to jump all the way down here. So let's say we decrease the exit pressure all the way to this the point where we get curve H. So curve H is where the exit pressure of the jet is equal to the atmospheric or the back pressure for supersonic flow, accelerating from the throat all the way through to the exit. Okay, so in this curve H, the flow is subsonic up to the throat. Then we hit Mach number 1 at the throat, and then it's supersonic beyond the throat. So just to reiterate, so now for this curve H, we have supersonic flow here. And as the area increases, what happens to the flow velocity? Increase or decrease? Increase, right? Which is the opposite of our intuition from subsonic flow. And so this curve H shows what we would call the design pressure. So this is the pressure that that we would achieve at the end of this diffuser section if we have purely isentropic flow throughout this entire device. So we've like matched. It's equivalent to like taking this like this exit atmospheric pressure and tuning it so that we've exactly matched the maximum Mach number that we could ever possibly get exiting from this diffuser section. That's basically what we've done in curve H. Because if we, let's say we have curve D, where the pressure is just a little bit lower than that curve C. At curve D, let's just stop there for a second. Are you with me through curve H? Let's not talk about these other ones yet. But are you with me through curve H? So for curves A, B, C, and H, what we've discussed so far for the isentropic flow relations would all describe what we see here. Okay, so what we've discussed so far describes A, B, C, and H. Okay, yep.
So just to make sure I understand, speeding up as you're opening
The area,
right?
not the throat. We're opening, so the throat here this is a fixed diffuser. So what's happening is as we move downstream, the area is opening up, right? It's getting bigger. Yep.
And then will there be shock waves that goes up into the atmosphere, or is that exactly the front of the atmosphere?
Yeah, in this case, there's no shock waves as it exists. Okay, for curve H, there's no shock waves. That's right. Okay. Okay, so if the exit pressure, if the back pressure is at the design pressure for our diffuser, then we don't see any shock waves. We see this nice isentropic flow all the way out to the exit. However, if we have back pressure greater than the exit pressure, we're still within this supersonic flow regime, right, where back pressure is less than this pressure at curve C, but greater than this pressure at curve H. Then we end up with the exit pressure, an exit pressure that's impossible to achieve in isentropic flow. So the flow cannot leave at our specified exit pressure. So if we're on curve D, right, if we're at this pressure here for corresponding to curve D, the flow cannot achieve the back pressure using purely isentropic flow. And so what actually happens, and we'll see this, we'll have a YouTube Friday again this Friday. I know it's been a few weeks, but we'll have an actual YouTube Friday. And we'll look at the operation of one of these diffusers as we change pressure. But what happens there is that a shock wave will form inside of the diffuser, essentially to match the pressure at the exit to the back pressure. And so we'll have a shock wave form somewhere within this diffuser section. That shock wave will increase the pressure. So as we move across a normal shock, we'll see that we always increase the pressure. It'll also take the flow from supersonic back to subsonic. And then our exit will actually be a subsonic jet at the back pressure, right? And that's for curves D and E and F. There's also a range of conditions shown here. Yeah, so for those curves where the back pressure is greater than the exit pressure, but we still have supersonic flow, through the end of the diffuser. There will be at least one shock wave that forms within the diffuser, which increases pressure to let final exit pressure match the back pressure. And then there's a range of pressures around this design pressure where we're just kind of off of the design pressure, and we end up with possible complex jet geometry and shocks external to the diffuser. So our next task is to discuss this kind of a shock. That's where we're going. We're going to talk about this kind of a shock and what happens to pressure, temperature, density, and so on, Mach number, when we have this kind of a shock, which we're going to call a normal shock because it is normal to the direction of flow. The shock wave is oriented normal to the direction of flow. These, what we're calling complex shocks that happen external to the flow, are beyond the scope of what we're going to cover in this class. Okay, but where we're going next is talking about this kind of a shock. All right, there's a lot here. Any questions on this? Yeah. Yeah, the exception is for this G and I. The exit pressure in G and I, the exit pressure is not exactly equal to the back pressure. And we just have shock waves forming external to eventually equalize the pressure. Yeah, naturally the flow kind of, yeah, you can think of it as the flow kind of wanting to match the exit pressure to the back pressure. Yep. So it's not always the case, again, that a supersonic jet has to match the back pressure. The exit pressure doesn't have to match the back pressure, but it is the the more stable state. It's the state that the system tends towards. Yeah. Okay, good question. Any other questions? Yes. We're about to talk about a shock wave. Yep. So okay, so you can think of this as, okay, we don't know exactly what a shock wave. We don't know how to deal with a shock wave yet. That's what we're going to develop now. Okay, we're going to develop the tools for discussing a shock wave. So this brings us to a normal. So you can think of that example as telling us like a shock wave happens, but now let's talk about what a shock wave is. So so we're going to talk about shock waves that are normal to the direction of flow. So this is the kind of situation in which we would typically encounter a shock wave. So where we have some flow upstream of the location of the shock, then we're going to, I'm just actually looking for an image of a shock wave to at least show you what one looks like, because we have seen one. So this, if we look here, this is a diffuser. I've been telling you that the Mach number was exactly equal to 1 here at the throat. The way I know the Mach number is exactly equal to 1 here at the throat is because here's a shock wave. This is what it looks like in this kind of a density gradient imaging. So we can actually see this shock wave forming here. Now there's more complex things happening against the walls, which are again beyond the scope of what we're going to talk about here. But there's a shock wave forming here. It's like an abrupt discontinuity in the density of the fluid. So the density of the fluid, the really strong signal here, shows us that the density of the fluid is abruptly changing as we move across that shock wave. So we need a way to handle this mathematically, analytically, and that's what we're going to work on now. So if we have the case here is we have some flow upstream of Mach number greater than 1. So we have supersonic flow. In this region here, we're going to say that the flow is isentropic. And we're going to have a shock wave which is not isentropic. All right, so shock wave, so shock wave is not isentropic. So we have an increase in entropy across the shock wave. And then downstream, we're going to end up with some flow which is subsonic, Mach number less than 1, and which is isentropic downstream, but at a new entropy, right? So we're going to have to consider that when we do our analysis. But let's talk about how we can handle first what's happening across the shock wave. A shock wave fundamentally is really just a large pressure wave So it's, I don't know if you've ever experienced a sonic boom or something going past, that's a shock wave. And you hear it as a big boom. This is this big change in pressure that comes past and, could hurt your ears if you're close enough, but the shock wave is strong enough. And so, so because this shock wave is really just a large pressure wave, we've already done some analysis for pressure waves. That's how we determine the speed of sound back earlier in the chapter. We're actually doing the same basic type of analysis, or we do the same basic type of analysis here. So again, this starts with the balance and state equations. We have continuity, we have momentum, we have energy, we have our perfect gas expression, and our constant specific heats. Notice here in the continuity expression, so I'm looking at continuity across this shock wave, and we're assuming the shock wave is really, really thin because it tends to be, it looks like a discontinuity basically in density and pressure. We're assuming it's really, really thin. So we're assuming the area upstream is equal to the area downstream, which is why area is dropped out of here. Okay. The expressions that we're going to use are fundamentally derived from our balance equations. We're not going to go through that full derivation here, but we can solve those balance equations to first determine the difference in enthalpy across the shock wave. We use the perfect gas equation of state. Using the perfect gas equation of state, we can then find the ratio of densities across the shock wave. So density changes abruptly across the shock wave. We know that from our visualization. That's how we visualize it, by looking at density of the fluid. This is now telling us what the density difference is, at least as a function of the pressure difference across the shock wave. And then by putting that together, we can then figure out the difference in entropy across the shock. Right? Remember, the shock wave is increasing entropy, right? Increasing disorder across the shock. And now we use these expressions to find properties across the shock. And I'm skipping through this to get to the next piece, which is going to be the one that's most useful for solving problems, right? So we may want to know, for example, the difference in entropy across the shock. But in order to get there, we're going to need what we call the Mach number relations, which are on the next slide. I see some people still frantically writing, so I'll give it a second before I flip. Okay, so the end result of our analysis, starting from the balance equations and equations of state, are that the ratio between all of the properties that we care about, the pressure, the density, the temperature, and even the ratio of Mach numbers across the shock, we can rewrite all of them in terms as a function of just our specific heat ratio. Right. So again, this is for a perfect gas. We have constant specific heat ratio. So it's a function of our specific heat ratio, K, 1.4 for air, and the Mach number upstream of the shock, the supersonic Mach number upstream of the shock. So for example, for pressure across the shock, P2 over P1 is this function of that upstream Mach number. This tells us, if you work this out and figure out what sign, K is greater than 1 and work through all this, P2 is always going to end up greater than P1. And this comes down to basically thermodynamics, which tells us that the Mach number 1, the Mach number upstream, in order to have a shock wave like this, the upstream Mach number has to be greater than 1. So these are shocks. When we're talking about normal shock waves, it's always from supersonic to subsonic flow. This is incidentally how I knew in that image that we just flipped back to, where there's a shock wave happening within our diffuser section. I know that the flow upstream of that shock wave had to be supersonic, because the shock wave like that will only form when the Mach number is greater than 1. We can use the same kind of relationships to solve for downstream Mach number. So downstream Mach number here written as Mach number 2 is this function. Again, it looks ugly, but this is really just an algebraic expression of K, 1.4 for air, and Mach number 1. Yes. A normal shock wave always brings you from super to subsonic. So there could not, so without accelerating the flow further, there could not be a second shock wave downstream. But if you accelerate the flow further, then you can have other shock waves downstream. We'll look at an example of that in the video on Friday. So if you had, for example, multiple throats in a system, then we can actually take the flow from sub to supersonic, across a shock, back to subsonic, through another throat, back to supersonic, across another shock, back to subsonic. So you can do that with multiple throats. But this, if you look at this expression and evaluate this expression for Mach numbers, again, Mach number 1 is always greater than 1. We'll see that Mach number 2 is always less than 1. Across the normal shock, we always go from super to subsonic flow. For K is greater than 1, which is always true. So for example, air is K is 1.4. So we can think of a shock wave, a normal shock wave, as nearly instantaneously transforming the flow from super to subsonic. Right, so it's like this instantaneous, like very thin region where we go from supersonic to subsonic flow. So I suggest you not try to write all of this down right now. It is on the slides and in the text, and you may make a mistake by copying it down. Also, I'm going to show you a maybe easier way of solving problems with Mach number with normal shocks. But we can use the same expressions to solve for all of our balance equations and equations of state to solve for our changes in other properties across the shock wave. So density changes, the temperature changes. Note that the density change actually gives us the change in velocity as well, by our continuity equation. So we're assuming that the area, that the shock wave is very thin. So area 1 is equal to area 2, just immediately where the shock is. So we can actually use continuity to figure out the ratio of velocities across the shock. We also have differences in temperatures across the shock. From this, we could figure out the new speed of sound, right? Speed of sound changes across the shock wave. Speed of sound is a strong function of temperature, and so we could use the temperature downstream to figure out the new speed of sound. Stagnation, temperatures, and pressure. So these are not too dissimilar from what we saw. The form is very different from isentropic flow. This is not too dissimilar from what we were doing in isentropic flow. But some important differences are that across a shock wave, because it is not isentropic, right? Because entropy increases across the shock wave, stagnation pressure, stagnation density change across the shock wave. Okay. So meaning if you take a flow upstream of that shock wave, if you take that flow and isentropically slow it down to 0 velocity, bring it back to stagnation pressure, you'll get a certain value, P01. And then downstream of the shock wave, if you take that flow and isentropically slow it down to stagnation, you will get a different pressure. Okay, so stagnation pressure changes across the shock wave because of the increase in entropy. Entropy. Another note is that A star, so the area at which the flow would achieve Mach number 1 if we accelerate it isentropically, it changes across the shock wave as well. So A star changes across the shock wave as well. Okay. And again, this has to do with the fact that a shock wave is not isentropic. Okay. So across the shock wave, we have new stagnation pressure, new stagnation density, new A star. All right, so we're just about out of time today, but I just want to talk for a second about solving just a general way to solve a normal shock problem. You'll see this kind of thing on your homework. So if we have flow from 0 to 1 to 2 to 3, and we know that there's a shock wave happening here, and we're going to go from 0 to 1 using our isentropic flow relations. We're going to jump from 1 to 2 using our normal shock relations. And then we're going to go from 2 to 3, again, using isentropic flow relationships. And for solving normal shock problems, you can use those equations that are defined on the previous slide, or you can look it up in, again, a table. This is table B.2, and these are the normal shock relationships, right, that are going to help us get from this point 1 to point 2. All right, thank you all, and I'll see you on Friday for our last YouTube Friday of the semester.